Phase diagrams. These are an essential part of understanding systems in chemistry, physics, and other sciences. So today I'd like to introduce you to them. Let's get right into it. First of all, we'd like to define a phase diagram. So what actually is this thing? And we can do that in terms of temperature and pressure. You'll see how that works in a minute. Our second goal is to understand Gibbs's phase rule. You might hear me say Gibbs a lot because I'm such a hardcore gamer and all that. The third thing is to analyze some real phase diagrams that relate to physical, chemical, and geological systems in the real world. I'm primarily a geologist, so I might tend to focus on geological examples, but I'm planning to do some future videos, and each one will focus on physics, chemistry, or geology, or perhaps even some other topics in science or engineering, where I'll go through specific examples of phase diagrams that are helpful in those fields. Now, when I was designing this PowerPoint here, I chose this theme because it reminded me of woodblock printing, which is something I'm absolutely fascinated by. So here's one of the most famous woodblock prints of all time, Hokusai's Great Wave from Japan. I want to come back to this near the end of the presentation, because there's actually a lot to say about phases and phase diagrams from pictures like this. Right now we need to address that first goal, so what actually is a phase diagram? Well, I looked around on the internet for a simple definition, and this is the simplest one I could find. A phase diagram is a type of graph that shows all the possible states of a system that are physically and chemically distinct. Those states are called phases, and the phase diagram also shows which phases exist or coexist and under what conditions. So what does that all mean? Let's take it apart a bit. To understand a phase diagram, we first should work out what a phase is. You might already know this. In a very broad sense, the different states of matter of a substance are phases. Water, dihydrogen oxide, has three different phases that we know as ice, water, and vapor. There's also plasma that you might know about. They all have the same chemical structure and formula. They're H2O, dihydrogen monoxide. That being said, a given substance can have multiple different phases that are all within the same state. So, for example, water has 5 different phases that are all solids. They all form under different conditions. Another way of saying this is there are 5 different types of ice that all have the formula H2O. It's pretty crazy, right? Now, I say they form under different conditions, so what exactly are those conditions? What determines which phase that we have? Well, one of those conditions is temperature. This one should be fairly obvious. I mean, you get between different states of water by raising or lowering the temperature. You take some ice, you raise its temperature, it melts, and you get liquid water. If you do the reverse, you take liquid water and you cool it down enough, it solidifies to become ice. So temperature is one of the conditions that affects which phase you have in a particular system. The other major condition is pressure. And this is a little bit more subtle. It turns out that if you change the pressure of a substance, it also changes to a different phase. To actually construct a phase diagram, you start out by making a graph of pressure against temperature. You plot temperature on the horizontal axis, and most people do that in degrees Celsius or kelvins if they're working in physics. And you plot the pressure on the vertical axis. I've done it here in kbars, which is a unit you may not be familiar with. Depending on your field, you might use kilobars, bars, gigapascals, millimeters of mercury. It doesn't really matter. What matters is what we do next. That is, we plot the different phases on here. So each phase is drawn as an area on the pressure-temperature graph. And these areas are bounded by lines. So for example, we have a solid phase here and a liquid phase. This just happens to be the phase diagram for iodine. I chose it because iodine's purple and I love purple. Now the really key thing about any given phase is that it is physically and chemically homogeneous. At any point within the solid area, the physical and chemical characteristics are exactly the same. Same with the liquid area. Any point within this purple area is the same, it's homogeneous. But the solid and the liquid have some major physical or chemical characteristic that separates them from each other. What does this all mean? Phase diagrams can be used for a variety of things. One of the really cool ones is they display phase changes or state changes. So for example, the solid and the liquid areas are divided by this line. If you cross that line from solid to liquid, that's the same as melting the substance, increasing the temperature. You can also do it by decreasing the pressure, as you see. If you took a point here in the solid area, you decrease the pressure and go down this axis, you end up in the liquid area. That's actually the case for the majority of substance. You decrease the pressure, you can melt the substance. The reverse of that is freezing. So you either decrease the temperature or you increase the pressure to move from the liquid to the solid area. There are a few key terms we need to get our heads around. And these are terms that you may have heard before in other contexts. They mean very specific things on a phase diagram, so it's important not to get these mixed up. It's okay, I'll walk you through it nice and slowly. First of all, we have this thing, a divariant area. Those are the areas I was just talking about. So an area within a phase that isn't near these lines here. Within a divariant area, we can change the temperature or the pressure, and the system does not change. It stays in the same phase. So here is an area here where this brown box is. Within here, we can change the temperature as much as we like. We can change the pressure as much as we like. But no matter how we do that, in this area, we always have phase 1. The phase does not change no matter what we do in here. Since we can change temperature or pressure, we have what we call 2 degrees of freedom. So being able to change temperature is a degree of freedom. Being able to change pressure is a second degree of freedom. The term degrees of freedom is fairly important. You don't need to worry about it too much. It's just that there's a formula later on that involves it. Let's move on. A univariant curve is another name for those lines between the phase areas. At any point along one of these curves, the two phases on either side of it are coexisting. So on this line, phase 2 and phase 3 can coexist, but only along this line. To keep the system from changing, we have to change both the temperature and the pressure to stay on the curve. If you just change the temperature, you move away from that line. If you just change the pressure, it's the same deal. So you have to change both of them to stay on the curve, and that means you only have 1 degree of freedom. Again, along this line you have phase 3 and phase 1 coexisting. You have to move along the line to keep them both coexisting and keep the system in the same state. Finally, we have an invariant point. This is where 3 or more phases coexist at one unique point. On this phase diagram, it's right here, where those lines meet. At this point, phase 1, phase 2, and phase 3 can all coexist. They're all stable. But if you try to change the temperature or pressure in any way, it will alter the system. If you just increase the temperature, you only end up with phase 1. The other two phases cannot exist. If you move this way, you only have phase 2. This way, you only have phase 3. You can move along any of these lines, but one of the phases will drop out. So to keep the system the same, you have to stay on that invariant point, and that means you have 0 degrees of freedom. Where am I going with all this? It's all about to come together, as you'll see, because we have this lovely formula. This is Gibbs Phase Rule. It's a formula that says F plus P equals C plus I. So what on earth does that mean? Well, F is the number of degrees of freedom that you have, and P is the number of phases. On that last phase diagram we looked at, we had 3 phases, and we had 2, 1, or 0 degrees of freedom depending on where on the phase diagram we looked. C is the number of chemical components that can describe that system. For example, the phase diagram of water has only one chemical component, and that's H2O. H2O is all the components you need to describe every phase on the water phase diagram, so it only needs one component. And I is the number of what we call intensive parameters. I called them conditions before, Basically, they are things like temperature and pressure that determine which phase you're in. And usually you have two of those. So we can rewrite the formula as F plus P equals C plus 2. This formula is incredibly useful to physicists, chemists, geologists, anyone else who works with phase diagrams, and let's see why. Here is a real phase diagram from a geological system. This is called the Aluminosilicate phase diagram. Now in geology, phases tend to be things like minerals that have fixed crystalline structures. On this diagram we have three minerals. Andalusite here, we have kyanite, which is a high pressure phase, and we have sillimanite, which is a high temperature phase. And each one occupies its own little area. All these minerals have exactly the same chemical formula, Al2SiO5. That's aluminosilicate. So that one chemical formula describes the whole phase diagram. There is only one component in the system. I wanted to show you some pictures because these really are quite spectacular minerals, and like I said, I'm a geologist. The kyanite here, pretty nice blue color, forms these nice blades. The name was originally cyanite, cyan meaning blue. Just amazing. This is sillimanite, that high temperature phase. In microstructure it forms like really thin needles or fibers. It's really cool. And andalusite forms these really amazing cross patterns in it. Now, let's try to use Gibbs' phase rule to analyze the aluminosilicate phase diagram. First of all, let's consider a divariant area. This area is within the sillimanite phase field. Now, as we said, with a divariant area, you can go any way you like in that area, and the system doesn't change. You still have the same phase. So every point in this area, you just have sillimanite. As we discussed earlier, we'd have 2 degrees of freedom because we can change pressure or temperature as much as we like. P, the number of phases, is 1. That one phase is sillimanite within this area. And the number of components is 1 because all these phases are made up of aluminosilicate. Now, we can substitute these numbers into this formula, and what we get is 2 plus 1 equals 1 plus 2. Hopefully you can see this is a true statement, so the equation holds. Gibbs' phase rule is correct. Now suppose we didn't know one of these things. Suppose we didn't know how many phases were actually in this phase diagram. We could use Gibbs' phase rule and the information we know to figure out how many phases there are, or the number of degrees of freedom, or the number of chemical components in the system. And that's actually a really powerful tool for scientists. We can go further. We can consider a univariant curve. So for example, this line that separates the kyanite and the sillimanite areas. The number of degrees of freedom on a univariant curve is 1, because we have to change pressure and temperature together to stay on that line and keep the system from changing. The number of phases has increased to 2, because kyanite and sillimanite are both stable along this line. And the number of components is still 1. We haven't actually changed the composition of the system. If we substitute these numbers into the formula, we get 1 plus 2 equals 1 plus 2. So again, Gibbs' phase rule holds. This is a true statement. Finally, there is an invariant point on this phase diagram. At the invariant point, there are no degrees of freedom, because even a tiny change will alter the composition of the system. The number of phases is 3, because kyanite, andalusite, and sillimanite are all stable at this one point. And the number of components, chemical components, is still the same, Al2SiO5. And again, the formula gives us a true statement, 3 equals 1 plus 2. So, that's an introduction to Gibbs' phase rule. Now, I wanted to come back to this design by Hokusai, the Great Wave. Like I said before, I'm pretty fascinated by the process of Japanese woodblock printing. And there are a lot of phases involved in this. It's an incredible process, really. I think I'll link to a video so you can see how it works. First you have paper. I believe it's called Gambi paper. That would be a phase, or the organic molecules in it would each constitute a phase. Then you have a whole variety of inks and pastes. Each ink is made from a different pigment, and each pigment contains different phases, slightly different chemicals that give it a unique color, hue, and texture. And then you can consider the actual, the content of the image itself. You have this wave, you have seawater. So water is a phase. The salt that's in seawater is also a different phase. You have people here, you have boats made of atoms and molecules and a whole myriad of different phases. Then you have the various molecules that make up the air and the sky, water vapor and the clouds up here. It goes on and on. So everywhere you look you can see phase relationships, phase changes, and applications for phase diagrams. With all that out of the way, what's next? Well, I hope I've convinced you that phase diagrams are useful and pretty fascinating, and relevant to science and life. So I'm going to make some more videos with specific examples where we'll properly analyze some phase diagrams from the fields of chemistry, geology, and physics. If you'd like to know more, there are plenty of other great videos on YouTube. Or you can head to the library and look out for science textbooks. Geology, chemistry, physics, engineering, they are chock full with phase diagrams. Thank you very much for watching, and I hope you'll stay tuned. See you later.